Hi, and welcome to another video by Emily Learning. So in this video, we'll be talking about what is tested in the topic on light in O-level physics. So let's get started. The best way to look at what is tested in O-level physics is to look at the syllabus. So here we are at the syllabus. So I'm now at the section on light. So let's find out what you need to know for this chapter. Okay, so first, candidates should be able to recall and use the terms of reflection, normal, angle of incidence, and angle of reflection. So first, let's talk about reflection. So reflection is basically the light getting bounced off from a surface. Okay, so when we are talking about reflection, there will be a normal. So normal is perpendicular to the surface. Then I have the angle of incidence here, which I denote I, and the angle of reflection, which I denote R. And when we have reflection, I is equals to R. The angle of incidence will be equals to the angle of reflection. Okay, so you need to state that for reflection, the angle of incidence is equals to the angle of reflection, and use this principle in constructions, measurements, and calculations. Okay, so you need to be able to draw the reflection diagrams, okay, and also be able to apply the concept I equals to R. Okay, next let's look at refraction. So the refraction refers to the bending of light as it um, due to the change in the speed of light as it moves from one medium to another with different optical density. Okay, so and whenever we have refraction, so let's assume that I have a solid glass block. Okay, and here it is air. Okay, so this is the incident ray, and this is the angle of incident. So when it moves from air, which is less dense, to glass, which is denser, the light rays will bend towards the normal. Okay, so this will be R. Okay, and this R here is the angle of refraction. Okay, and there's this formula: refractive index is equals to sine I over sine R. And refractive index is also equals to speed of light in vacuum over speed of light in that medium. Okay, so in other words, if you are looking at refractive index of glass, then the medium here will be speed of light in glass, and so on. All right, so we've covered D and E. Next, let's look at critical angle and total internal reflection. So I do have a definition for critical angle. I'll provide you with the where you can look for it. So it is found here. Okay, so whoops. Okay, so critical angle is the angle of incidence in the optically denser medium, for which the angle of incidence in the optically less dense medium is 90 degree. Okay, and the definition of total internal reflection, um, and what is total internal reflection? Well, total internal reflection occurs when two conditions are met. Firstly, the angle of incidence is greater than the critical angle, and secondly, the light is moving from an optically denser medium to an optically less dense medium. So these two conditions must be met in order for total internal reflection to take place. Okay, so take note of that. Okay, so basically this is what you need to know: total critical angle and total internal reflection. Okay, so maybe let me say, so this, okay, let me change the color as well to maybe blue. Okay, so let's assume that this is the critical angle. So when it is the critical angle, okay, the, so critical angle, so this is critical angle because critical angle occurs when the angle of when the angle of refraction in the less dense medium is equals to 90 degree. And whenever you have an angle greater than critical angle in the optically denser medium, then total internal reflection takes place. So let's look at this. So I have this glass block here. Now, this angle is greater than critical angle. So when that happens, light will not be refracted. Instead, it will undergo total internal reflection. And this angle here will be equals to this angle here, because reflection, angle of refraction means that when we have reflection, the angle of incidence and the angle of reflection is always the same, right? So these two angles will be the same. Okay. So optical fibers, they are an application that makes use of total internal reflection. So we send a signal into the optical fiber, and this signal undergoes total internal reflection, so as to send the signal from one position to another. Okay. Next, we'll be looking at converging lenses. Okay, and you also need to know how to draw the ray diagrams for converging lenses. Okay. Okay, then you need to be able to define the focal length of a converging lens. So you can find the definition here. I do have the definition. So focal length for a converging lens is defined as the distance from the optical center of the lens to the focal point on the principal axis. Okay. You also need to be able to draw the ray diagram to illustrate the formation of real and virtual image of an object by a thin converging lens. I'm not going to go through this in detail, but what you need to do is whenever you're drawing a ray diagrams, okay, let's assume that this is the object, this is the lens, and this is the optical center. So this is the center of the lens, all right? Okay, so what we need to do is remember the rules when you are drawing the ray diagram. So a light ray that passes through the optical center will go undeflected. So I will draw a line from here and it will pass straight through. Okay, then next let me label the focal point. So if I have a light ray that is parallel to the principal axis, this is the principal axis, then it will pass through the principal focus. Okay, or it'll pass through the focal point. Okay, so when these two points converge, that would be where the object is. So when these two rays they intersect, that is where the image is. Okay, sometimes the rays do not intersect behind the screen, it intersects at the other side. Okay, when that happens, instead of having a real image, you have a virtual image. All right, so that's all for this chapter on light.